Hello everyone. In this tutorial, we will talk about graph traversals. The first traversal that we will discuss in detail would be breadth first traversal, and in the next tutorial, we will discuss about depth first traversal. Both of these traversals are really important when you are solving problems related to graphs, and they have many real life applications. But before we get started, make sure to check out free masterclasses on Scalar's event page to learn from some of the best industry experts. Link is in the description below. Let's begin with the tutorial. So let us talk about graph traversal first. What is a graph traversal? So graph traversal, also known as graph search, is a way or is a process of visiting each vertex in a graph. Such traversals, as I told you, are classified into two types. One is BFS, which stands for breadth first search, and it is a iterative way to traverse the graph. And second one is a recursive way called depth first search. In this tutorial, we'll focus on BFS and its applications. So BFS actually has many applications, and one of the most commonly used application is finding shortest paths in undirected graphs. We'll also look at such applications in this tutorial. So let us start talking about BFS. So it is a technique for traversing a finite graph. That means the number of nodes in the graph would be finite. And the way it works is it visits the sibling nodes before visiting the child vertices. So what does it mean? If you have something like a node A and it has children like B and C, and then you have some children like D and E, and so on. So the way it works is if you look it in the form of a tree, suppose this graph is a tree. Now this is not a tree because I'm added one more edge here. So the way it works is it will visit this node, then it will come at B, but it will visit sibling of B, that is C next. So it will visit BC, then it will visit D, E, F, G, and so on. So in a way, if you look at in the form of a tree like traversal, it is like a level order traversal that we have done in a tree. But in a graph, it will be quite similar, but there is one catch. The catch is graph contains a cycle, right? We have to make sure that we are not visiting a node which is already visited. For example, from this node 1, if you visit 2 and 2 is connected with 3, 3 is connected with 1, so there is a cycle. So if you say okay, I'll visit 1, I'll visit children of 1, that is 2, I'll visit 3. From 3 now you cannot go and visit 1 again, right? So this is something we have to make sure is handled properly by our algorithm. So before I dive deep into the algorithm or into the code, let us try to understand some applications of BFS. BFS is can be used to find all the vertices within a connected component. So we want to see what parts of the graph are connected. It is also used to finding shortest path between two vertices in case of a undirected graph. That means all the edges, sorry, unweighted graph. That means all the edges, they have equal weight. There is no weight assigned to any edge. If it is a weighted graph, then we have to use a different algorithm. It can be used to check a graph for bipartness. It can be used for cycle detection in undirected graphs. It is also used in Ford-Fulkerson algorithm for maximum flow. It is also used in serialization, deserialization of binary tree. It is also used in maze generation algorithms, and it can also be used in algorithms like flood fill. So there are many applications, and that is why understanding this algorithm becomes very important. So let us now dive deep into the algorithm. Now suppose a graph like this is given. So what kind of graph it is? In my case, it is a unweighted graph, and it is also a undirected graph. That means edges don't have any specific direction. If 0 and 2 are connected, 2 and 0 are also connected, so we can go both sides, right? So now in this algorithm, what is the input? The input is a source vertex. That means you are given a starting point. From that point, you have to traverse the whole graph. The starting point could be 0, it could be 3, it could be 6, it could be any node. So just to keep things simple, I'm going to take 0 as my starting point, right? And let me also draw the adjacency list that could be possibly input for this algorithm. So that means 0 is connected with 2 and 1. 1 is connected with 0 and 4. So neighbors of 1 are 0 and 4. Neighbors of 2 are 0, 3 and 4. So 0, 3 and 4. Neighbors of 3, they are 2 and 6. Neighbors of 4, they are 1, 6, 5. So I'll write it as 1, 5, 6. Then I have neighbors of 5, which are only 4, and neighbors of 6, which are 3 and 4, right? One thing I told you, that if you start from this node, right? So what we need to do, we'll be using a queue in this algorithm. You will understand why this queue is going to be very, very helpful. Let me draw a data structure here, which is a queue. Apart from it, we will also need something to maintain whether a node has been visited or not, right? Because the graph contains a cycle, and it is possible that we are coming to the same node again and again, right? So this is a queue. It is a empty queue as of now, right? The queue, you know, it has a FIFO property, first in first out property, right? So it is a FIFO queue here, and apart from it, I'm making one more data structure, which is going to denote whether a node has been visited or not. So 0, 1, 2, 3, 4, 5, 6. I think this is sufficient. We don't need. So we will mark whether a node is visited or not. So right now it is nothing is marked, nothing is visited. We'll start from this node, that is the source node. Let's just assume the source node is 0. We'll mark it and we will put it into the queue. 0 has been visited, 0 goes into the queue, and I am going to mark it as visited. So here the circle denotes the queue has been visited. Now what you will do next? You will look at this adjacency list. You will find out the neighbors of 0. The neighbors of 0 are 2 and 1. So you will pop this node out. The node is 0. You will look at neighbors of 0, that is 2 and 1. You will mark them as visited and put them into the queue. So you from 0 you can easily visit 2 and you can easily visit 1. So what I'm trying to do is I'm marking 1 and 2 as visited, and I'm putting 1 and 2 into the queue. So first I visited 2 and then I visited 1. Both of them, they are into the queue. That means I've marked 1 and 2 as visited. Now what you will do next? Nothing. You simply have to pop out a node from the queue every time and do the same process again. So now you will remove 2. Look at the neighbors of 2, which are 0, 3 and 4. So now 0 is already visited. So you do not do any work at 0. Then 3 and 4. 3 is not visited. You can visit 3. So mark 3 as visited. Put it into the queue and mark 4 as visited and put it into the queue. Okay. Now 2 is gone. 2 has been removed. Next node you will get from the queue, it is going to be 1. So you will remove 1 from the queue and you will mark neighbors of 1 as visited. So neighbors of 1, 0 and 4. So look at 0. 0 is already visited. 4. 4 is also a neighbor. 4 is already visited. So you do not do any work. Right? So in the meanwhile, you can print the nodes that you have seen so far. So you have seen 0, you have seen 2, you have seen 1. Next, you will pop out 3. So remove this node, print this node, look at the neighbors 2 and 6. So 2 is already visited, do nothing at 2. 6 is not visited. So mark 6 as visit, put it into the queue. So you have traversed 6 as well. So 6 is now also into the queue. Next, you will pop 4. So print 4, look at neighbors of 4. So 4 neighbor is 1, which is already visited. Its neighbor is 5, which is not visited. So you will visit it, put it into the queue. 6 is already visited. Nothing to do here, right? Next, you will get 6 from the queue, remove it, print it, and now look at neighbors of 6. 6 neighbor is only 3 and 4, right? But both of them, they are visited, so you will not do any work. So next you will remove 5. 5 neighbor is 4, so this is also removed. 4 is already visited, hence you do not do any work. And now what you can say is that your traversal is done, right? Your traversal is done. So what happened during this traversal? So we visited each node once, and in the worst case we are traveling through all edges once, right? So what we have done, like we have traveled through some edges, and we also checked that from 4 I can go to 1. So we did check this edge, right? We did check this edge. 1 was already visited, so we did not mark anything here, right? So we did not mark anything here. What I'm trying to say is, when you're running this algorithm, each vertex is going into the queue once, and it is coming out of the queue once. And when you're finding the neighbors of a node, you're traveling through all the edges, right? So all the edges are being covered at most twice. For example, neighbor of 4 is 6, neighbor of 6 is 4. So each edge is counted at most 2 times. So if I talk about the overall time complexity of this algorithm, it will be linear in terms of number of nodes and number of edges. This is what we are doing, right? So I hope you have understood the basic BFS idea. Next, we will look at the implementation and code this algorithm. So let us discuss the implementation of BFS. I already have the boilerplate code ready, which is basically adding edges into the graph. So the BFS function is something that I'm going to write now. So return type is void. We do not want to return anything. The method name is BFS, but what we may expect as input is one source node from which we should start doing the BFS for this graph. So this is the graph. So I told you we will be needing two data structures, one to maintain whether a node has been visited or not. So I can maintain a Boolean visited array, and this will be a array of size v, where v is the number of vertices in the graph. Next thing I will need would be a data structure q. So in Java we have q as an interface. So I'll create a linked list which provides me with the implementation of q as well. So linked list of integers, we will just call it as q, and I will say this is equal to new linked list. All right, so that are these are the data structures that we will be needing. Now let's start with the algorithm. So in the first step, what I will do, I will start with the source node, mark it as visited, push it into the queue. So I have to do three things. Mark it as visited, so visited of source is going to be true. So I will say okay, this is going to be true, and then I will traverse the neighbors of this node. So first thing I will do is I will push this into the queue. So I can say queue dot add last. The node is source. Okay. And second thing I will do is I will mark this as visited. The visited of source, this is going to be true. Now what can I do now? I can say while my queue is not empty. So I will stop once all the nodes have been popped out. So how do I add into the queue and remove from the queue? So if you have to add something into the queue, that addition will happen from the ending. So add last. And if you have to remove something from the beginning, so we can call remove first method. So I can say okay, the node at the front of the queue. So that is int node. This is going to be queue dot remove first. All right, now what can I do? I can say okay, for this node, the node that I've removed from the queue is 0, right? So I need to traverse what are the neighbors of 0. So 0's neighbors are there in adjacency list, so they are 1 and 2. So what I need to do, I need to traverse on these neighbors. If the neighbors are not visited, I will mark them as visited and I will push them into the queue. So this is what I do. So I can say okay, for every neighbor. Okay, so to get the neighbors, what we can do, we can use iterator. I can create a iterator of the type integer and call it something like iterate it, and now I can say give me the neighbors of this particular node. So if you know this is the adjacency list so I want to iterate on this adjacency list of the node. So I can say okay, while it dot has next, that means the next node is present. Basically it is a way to iterate on the adjacency list. Sorry, you have to call a method called list iterator because we are iterating on the linked list. So zeros neighbors are 1 and 2, right? So these are stored in a list which was a list object. So adjacency list of node is a list. We have to get the iterator using this method list iterator. So it will iterate over these nodes until the list is not finished. It will go over these neighbors. Now I want to get the node, right? So how do I get the node? I can say okay, the neighboring node is nothing but it dot next. That is the neighboring node. And now what I need to do, if it is not visited, if not visited neighbor, what do I need to do? I need to mark it as visited. I can say visited of neighbor, this is equal to true, and I need to add it into the queue. So I can say queue dot add last, and the item is neighbor. We are iterating over all the neighbors, and if the neighbor is not visited, we simply mark it as visited and we push it into the. So I hope this should suffice. And one more thing we can do in the while loop is we can print out the node. We can see what output do we really get. So I can say sout node. Now let us test our algorithm on the graph I have already constructed. So let me show you. In graph main I will go, and this is the graph, same as this graph, and now we are going to run BFS function on it. So I can say g dot BFS. Let's say the source node is 0. So let's go and run this code and see what output do we get. We should get all the nodes from 0 to 6 because we are doing a graph traversal. Let's see the output. Okay, we got an error, index 6 out of bounds for an array of length 4. Okay, so here we have to give, we have 7 nodes actually. Input needs to be fixed. Okay, so this is our adjacency list, and we are getting 0, 1, 4, 3, 6, 5. So we are getting all the nodes. That means the graph traversal is correct. Now the exact output will also depend upon the way you have stored these nodes. Okay, so you said okay, 0's neighbors are 1 and 2. After 0 it will print 1 and then 2. But if you say in my adjacency list I will store 2 and 1 first, that means I will add this edge before this edge. Then the output will be 0, 2, 1 and so on. So right now our goal was to visit all the nodes which can be reached from node 0. So we are getting 0, 1, 2, 4, 3, 6 and 5. That means this output is correct. We are able to reach all the 7 nodes including 0. Now let us discuss one application of finding the shortest path from the source node to all other nodes. Okay, so what we are going to do, we're going to do shortest path from source to all other nodes in a undirected graph, in a unweighted graph. Unweighted graph. So this graph is an example of an unweighted graph. So graph can be directed or undirected, but it must be an unweighted graph for the BFS algorithm to work for finding the shortest path. Right? So we are going to talk about BFS shortest path algorithm. So the algorithm is very simple and it is very similar to just doing BFS. So let us try to visualize what we are doing in BFS. We are starting from node 0 and we can mark the distance of 0 as 0. And from 0 we are visiting the nodes 1 and 2. Since we are visiting a node for the first time, we will be updating their distance and we will be saying this distance is 1 and this distance is also 1 because we are coming from 0 and 0's distance is 0. Next, in the queue what you have done, you have said okay 0 is there, then you pushed 1, then you pushed 2 and so on, right? Now next item you will pick is 1 and you will update the neighbors of 1. Neighbors of 1 is, let's say, 4 and 0 is already visited, so you will not go there. So you will say okay, since I am visiting 4 via 1, this distance must be 2. So distance of 4, I can say distance of the neighbor is 1 more than the distance of the parent. So parent is 1. Okay, so distance of parent node is 1, child node is 4, or the neighbor node is 4. 4's distance is 1 more than the parent. So I will visit 4 and I will push 4 into the queue. So next I will remove 2. So 2's neighbors are 0, already visited. 3 is not visited, so I can visit 3 and I can say okay, this distance is going to be 2. So I will push 3 into the queue, and 2's neighbors is also 4, but 4 is already visited, so we will not update it. So it is not possible that you are reaching a node later which is already visited and the distance will get minimum. It's not possible in case of a unweighted graph. If it would have been weighted graph, this could have been possible, right? Now 4 is already visited, and since you are reaching from 2, again node is already visited, so this distance will be either greater or equal to 2. So it is, we will not update it, so we will not do anything at 4. So 2 is done, 2 has done its work. Next we will pop out 4, and 4 can now update its children. So 4 children are 6, so this distance is 3, so you push 6, and 4 can also update 5, so this distance is also, you can push 5. Next you can pop out 3. Now 3 again, it will try to visit 6, but 6 is already visited, so hence you don't do any work. Then you try to pop out 6, so you can remove 6 easily, but there are no nodes, no neighbors of 6 which are not visited. Then you pop out 5, there are no neighbors of 5 which are not visited. So if you look at these values, you will find that these are the shortest distances from 0 to all these nodes. These are the shortest distances from 0 to all these nodes. So that means distance of 0 is 0, distance of 1 is 1, distance of 2 is 1, distance of 3 is 2, distance of 4 is 2, distance of 5 it is 3, and distance of 6 it is 3. So one observation we can make out from here is that BFS visits nodes in increasing order of their distance from the source node. This distance was 0. These two distances were 1. These two distances were 2. And these two distances were 3. Right? So this is an observation, right? So when I said you can get any ordering, so that means between these distances the ordering can change. So BFS might produce an output like 0 to 1. It might produce 4 3, it might produce 3 4. 5 6 might get 5 6 or 6 5, right? So different orders, but the distances of these nodes will be in increasing order from the source node. So that is how we can find shortest path from source to all other nodes in a unweighted graph by simply using the BFS. In the next part, we'll show you the code changes that we need to do for this algorithm. Though it is very simple, take a moment, pause the video, and think what changes you will make into the code. Alright, so let us discuss the code changes. So now, apart from the visited array, what you need to do, you need to maintain a distance array. The distance of each node from the source node. So you can say, okay, I need a distance array which is of size v, and in the beginning you can say distance of source. You can update that distance of source as 0, and rest is very simple. As you are visiting more and more nodes, you need to update the distance. So you can say, okay, I'm going to visit the neighboring node. So when I'm visiting this neighboring node, I can say distance of this neighboring node is 1 more than the distance of the node that is parent of this node. So that node is nothing but this node. So this node is distance of node. So that's it. Now what we can do in the same function, maybe we can either return the distance array or we can just print the distance array. So here I can say let's just iterate over the distance array for I equal to 0, I less than v, I plus plus. I can show the node which is going to be I, followed by the distance which is distance of I. So let's go and run this code and we should see we're getting node 0 at distance 0, 1 at 1, 2 at 1, 3 at 2, 4 at 2, 5 and 6 they are at distance 3. This is how easy it is to make changes in the code, and now we have made shortest path algorithm using BFS. Now some of you might be wondering that okay, we have figured out the shortest path, but we have only figured out the distance actually. What if I actually want to figure out the exact path from, let's say, 0 to some node 5, right? Maybe I want to find out what is the shortest path. Should I go like this, or should I go like this, or should I go like this? What will be the shortest path from source to destination in a unweighted graph? So again, this thing is very simple. So what we were doing BFS. 0 was visiting 1 and 2, 1 was visiting 4, 2 was visiting 3, and 3 was visiting 6. No, I think it was like this. 4 was visiting 5 and 6, and then 3, something like this we did, right? So now, again, if you want to find out the shortest path to reach 5, you will know that, okay, 5 was visited from 4, 4 was visited from 1, and 1 was visited from 0, right? What you can get, you can actually store the parent. So you can store parent of 5 is 4, parent of 4 is 1, parent of 1 is 0, and parent of 0 is, let's say, 0 or minus 1, anything you can put. What you can do, you can store these parents for every node, and then you can do trace back. You can say, okay, I'll start from 5, and okay, from where I should go. So this is my destination node. Who is the parent of 5? How do we arrive at 5? We came from 4, so I can go to this node. Okay, how do I came at 4? I came from 1, so I can go to this node. How do I came at 0? I will go to 0. Okay, how do I came at 1? I came from 0, so I go to 0. Who is the parent of 0? Minus 1. That means we have finished the entire path. In this way, you will be able to store 5, 4, 1, 0 in an array or in an array list. So this way you can also print the shortest path from the source node to the destination node. The only changes in the code you need to make is you need to create a parent array, and when you're visiting from a node to a neighboring node, so you can say, okay, parent of neighbor will be equal to node, something like this. And then you can simply put a while loop at the end. Once all the nodes have been updated, your BFS has been done, you can say, okay, while I don't get the source node, let me travel back from the destination node. So you will travel this way, and you will eventually reach the source node. So this is something you have to try, you have to figure out, you have to make the required code changes in the algorithm that we have discussed. Now we will discuss one application of BFS in solving a problem. So we are given a snakes and ladders board which looks like this, and what we need to do is we need to find out the minimum number of moves that are required to go from source, which is from cell 1, to destination, which is cell number 36. So first of all, we need to decide whether it is a graph problem. So if you look carefully, you can analyze that we can clearly see there are 36 vertices. There are 36 nodes where you can go. So clearly we see vertices. But how do we decide the edges, right? So basically the question says there is a regular dice. So on your dice, you can throw any number of your choice from 1, 2, 3, 4, 5, 6, right? So the rules of the board are very simple. Whenever there is a ladder, you can climb that ladder. But whenever there is a snake, you will be cut by the snake and you will reach the tail of the snake. So you can cut down from head of the snake and you can reach the tail, this position, right? So basically, like in any snakes and ladders game, you have snakes which can cut you down and bring you down, and there are ladders which you can climb and move to the top. The question is, how many minimum number of dice moves will be required to reach this destination? So you can assume there is only one player, it's not a two-player game. So the question is only about finding the minimum number of dice moves. We need to think carefully what kind of graph it is. If you analyze carefully, you will analyze that if you look at the dice moves, so at 1 you can throw a 1, that means you can reach 2, but at 2 there is a ladder, that means you will reach 15. So if I talk about this edge, there is an edge from 1 to 15 in this graph. Then if at 1, if you throw a dice 2, you can reach 3. There is an edge from 1 to 3 also. If you throw a 3 on dice, you can reach 4. That means there is a edge to 4 as well. And all of these edges are directed edges. And then if you throw a 4, you will reach 5, but on 5 there is a ladder. So that means the edge is from 1 to 7, right? And if you throw 5, you can reach 6. That means there is an edge from 1 to 6 also, right? Now if you throw 6, you can also reach 7. That means it is the same edge. We will not count that edge again starting from 2. So 2, there is a ladder, so we do not need to do anything. Then you go at 3. So from 3 again there are edges. So there is an edge from 3 to 4. If you see carefully, from 3 you can go to 4, and so on. From 3 you can go to 7 also. From 3 to 7 there is an edge, and so on. That means how many edges I have. So I have approximately 6 edges starting from each vertex from approximately 6 edges from each vertex. Okay, so if the vertex is v, I can go to v plus 1, I can go to v plus 2, I can go to v plus 3, v plus 4, v plus 5. This would have been the case if there was no snake and no ladder. But now what is happening is, suppose I go to v plus 1. Here there is a starting point of the ladder. So that means I will reach at some other position. So that means there might be a factor which will add up or which will be subtracted, and that factor will come from if there is a ladder at that position or if there is a snake at that position, right? That is what I'm saying, that it is an example of a directed graph. It is an example. Is it a weighted graph? The answer is no. It is an example of unweighted graph. That means all edges are equal, because the cost to cover any edge is dice throw. So it does not really depend what number you throw on the die. Each move is counted as one throw, right? So if you analyze carefully, you will see it becomes an example of a directed unweighted graph. And if it is unweighted graph, we can use the BFS shortest path algorithm to find out how do I reach this node, right? So in this case, if I analyze little more carefully, I will see from 1 I can go to 15. From 15 I can throw 3 and I can reach 18. 18 there is a ladder, I can reach 29. In order to reach 29, I just need 2 moves. Then I can throw 1 to reach 30, and then I can throw 6 to reach 36. So I guess in 4 moves I can easily finish this game. So I hope the problem statement is clear. Now it's your turn to figure out how do we construct such a graph, take input such a graph. So regarding input, you will be given the number of vertices, the number of snakes, the number of ladders, as well as the position of the ladder. For example, 2 to 15 there is a ladder, 5 to 7 there is a ladder, right? Similarly, positions of snakes will be given as pairs. 17 to 4 there is a pair, right? So take a moment to think, how do you input such kind of a graph and how do you make your BFS algorithm run on it. Alright, so let us discuss how we are going to build the algorithm. So I have written some boilerplate code. It's not the complete code. So I'm going to read some inputs. I'm going to ask enter the number of vertices, source and the destination. So I'm going to read these three things. After that, I will create a graph. Since I know the number of vertices, right? I can create a graph object, or I can do it later on as well. That's fine. And I'm going to read the number of snakes and their positions. So in our scenario, we have 1, 2, 3, and 4 snakes. Number of snakes in my case are 4, and these are the positions of the snakes, 17 to 4. So I'm taking in this direction, head to tail. So that means 17 to 4, if there is a snake, you look carefully, 17 to 4, this is the snake. Similarly, I'm reading the letters in this direction. 5 to 7, there is a letter. So 5 to 7, there is a ladder. Now the question is, how do we handle this data? What should I do with this data? So first of all, I need to read this and I need to make sure that this data is used in my construction of the graph. Earlier we were creating a hard-coded graph, so we'll not do that thing here, right? So we'll create our own graph. So first thing is, here I'm just reading the number of snakes. I'm not reading what snakes I have. So I need to implement logic for that as well, right? This part I'm going to do it right now. So let's try to understand how we will actually create a graph. So we'll create a graph object C, and we will, of course, we'll try to add edges to it. Add edge. Now in edge, you need to know that from where the edge starts and where the edge ends, right? And it is a directed edge, so it's not a undirected graph. So I will set this third parameter as false. So now if I talk about vertex 1, so I told you from 1 I can go to, let's say, vertex I can go to I plus 1, I can go to I plus 2, I plus 3, I plus 4, I plus 5, I plus 6, and plus something, right? This value could be 0, this value could be positive value, this could be negative value. What is this something going to be? It will depend upon whether there is a snake or a ladder starting from that position. For example, I plus 1. So at 2, I have a ladder which gives me, which actually takes me to 15, right? Which is actually taking me to 15. That means I'm getting a jump of 13, right? So for example, if I is 1, I take a move of 1, I reach 2, and 2, there is a ladder which is giving me a jump of 15 minus 2, right? So basically there is a ladder So the delta that is given by the ladder, right? So if I go to, let's say, I plus 3, so there is no ladder here, so this delta will be 0, this delta will be 0. I plus 4, I reach 5. At 5 I actually reach 7, so this delta is 2. How do I compute this delta? This delta I have to compute and store it in an array. I have to compute and store it in an array. So that means in an edge, this becomes the starting point and this becomes the ending point of the edge. So this delta is very easy to compute. For example, you are given there is a ladder from 2 to 15. You can easily say, okay, I'm going to store it in some kind of array. Let's create a board array, right? So it's a 1D array of 36 positions, and in each position I'm going to store a delta. If someone says, okay, there is a ladder from 2 to 15, that means at the second position in this array I can store 15 minus 2, that is 13. So at the second index in this array I can store 13. So if there is a snake at let's say 32, which takes me at 30, let us assume this index is 32. So at 32 I get a delta of minus 2. So if I reach 32, effectively I reach 30. So 32 minus 2. So this is how I'm going to do it. So once all the edges have been inserted into the graph, I can easily run BFS on it. So let us try to insert all these edges into our graph. So what I'm going to do, I'm going to run a loop. Let's say for I equal to 0, I less than snakes, I plus plus. I can say, okay, snake has a head and snake has a tail. So I'm going to read these values. So I can say head equal to scanner dot next int, tail equal to scanner dot next int, and I'm also going to create a board array. So the board array can be created here. So int board, and this is equal to new int. How many? So I'm going to do v plus 1 because it is a 1 based indexing here. So I've created a board array. Oh, I have to move this code here because v is not input yet. So this board array will come here, or you can do it like this. That's fine, that's fine. Board array is now created. So now when I'm reading the snakes, right, so I have to update the board array. So I can say, okay, board of head. So in case of snake, the snake is going to bite from the head, right? So board of head will store a value that is equal to, because now it is giving you a decrement. So from 17 you are going at 4, right? Let's look once again. From 17 you are going at 4. So board of 17 should say that my value is nothing but 4 minus 17. So this value should be minus 13. So this is how it should be. So it should be equal to tail minus head. So tail is a small value, head is a large value. So this value needs to be negative. This will update the board array for snakes. Similarly, we need to update the board array for ladders, and we will utilize this array while constructing the graph. I will show you how. Make a similar loop. I have the ladders. Instead of snakes here, I will have ladders. Now the ladders are given in this fashion, bottom to top. So ladder also has a head and it also has a tail. So tail is, this number is smaller, this number is bigger. Tail minus head would be a positive number here. That is fine. So I think board array looks fine. So I can just display you the board array as well. So I can say s out arrays dot toString, and I can give the board array. Now I have this board array, I have these delta increments. Again, I need to figure out how do I insert all the edges. Now that thing is fairly simple. You need to go to every vertex and create the next 6 edges that will start from that vertex. For example, if I start from 5, or if I start from I can go to I plus 1 plus board of this position that you have reached. If you do 5 plus, let's say, some number 5, or 5 plus 4, you reach 9, but 9 is not the end position. You actually reach 27, right? I plus 2 plus board of this position, I plus 3 up to I plus 6. Basically from ith node where I can go. So here I'm going to use the board array to decide where I can actually go. So this will be board of I plus 1, board of I plus 2, and so on. So let's see here as well. So let's create the graph now. So I have graph G. How many vertices I have? I have V vertices. So I'll just keep V plus 1 because it is 1 based. So we are also adding 0 here. This is equal to new graph. New graph of V plus 1 vertices. Alright. I have to add edges, right? So I can say, okay, for int, let's say source, which starts from, or let's say I'm going to add edge from I to something. So I to some j. Okay. So if I goes from, I can start from source, which is 1, the smallest node. I can go till less than destination, that is my last node, I plus plus. So I'm going at every node. Then I can throw a dice at every node. I can throw 1, 2, 3, 4, 5, 6. So I can throw a dice. Dice can take a value 1. The maximum value dice can take is 6. And I can say dice plus plus. So what is the node at where I'm reaching? The jth node is I plus dice, right? But this is not final. I also have to add delta. So I can say, okay, j equal to j plus board of j. In this value, what I'm saying is from I you throw a die, you reach I plus dice. Now at this position, it is possible that there is a ladder. The ladder gives you a jump of 13. So you have to add this factor also that is stored in board of j. But if there is a snake that takes you down, so you have to decrement this value also. That addition subtraction is already handled in the board array. Now if j is less than equal to destination, that means I do not want to add any edge that goes out of the board. So I can say g dot add edge. So u is my I, v is my j, and it is not an undirected graph. So this value is going to be set to be. This completes the graph creation process. Now what we need to do, we need to run BFS algorithm on it. So as you know, we have already implemented the BFS algorithm. I'll just copy this code and tweak it a little bit so that we can do it for this particular problem. So I can say BFS dot s path. So in this case, I'm getting source. I'm also getting the destination. So if the user is interested in finding out minimum number of moves, so you do not need to print distance every node. You can simply return the distance of destination, and you can change the return type to integer. This can be done. Now one thing might ask is, user might ask you to give the path also. So as I discussed with you, along with the visited array, you can create a parent array as well, and you can say, okay, this is equal to new integer of v, and here you can say, okay, for first node, that is my source node, the parent is, let's say, -1. So parent of source, this is -1, or you can set this is the source itself, something like this, so that you can know, right? Right now I'm just saying this is going to be -1, and whenever you visit a node, you can set the parent of neighbor is going to be the node. Now, as I told you, you can backtrack and you can find out the complete path as well. Let us discuss that thing as well. If you want to do the path printing, that is fairly simple. You can start from the destination node, let's say 36. Now 36 nodes from where I was visited. So maybe the parent of 36 is 30, right? So I can start from this node, reach this node, again ask the parent, go back, and so on. I can trace the path until I hit 1 or -1, something like that. So I can say fine, I take a temporary value which is destination, and I can say while parent of destination or while parent of temp is not equal to -1, what do I do? I say, okay, fine, I will print out the destination. I will print out the temporary node. So basically what I'm saying is, the temporary node is this. Temporary node is 36. I will print it out and I will go here. This will become the new temporary node. But how do I update this temporary node? So fairly simple. Temp equal to parent of temp. At every node, I take it back to the parent. So this is basically going back to the previous node in the path how it was discovered. Then I'm saying return the distance of the destination. Now let us go and run this code. I think it should be fine. Yeah, it seems fine. So let us try to execute the code. So I've given the input, I've just combined the input and I'm giving it, but now I'm getting a error. Actually, I will tell you what is the error. So it is saying exception in thread main, index 38 out of bounds. So in main, this is the array. So this is going out of bounds. Why this is happening? Because if you add something to, let's say, node 35, you say, okay, I will take a jump of 3. You will actually reach 38. So actually I'm checking it here. So instead this check should be done here, right? So when I'm doing this value, when I'm computing this j, so I should do this thing here. If j is less than equal to destination, then I should do j equal to board of j. And again I should check if j is, you can do it here. Yeah, that is fine. So if j is now less than equal to destination, then you can actually add that edge. I think this would be okay. Or you can do two conditions here, right? So you need to check that. See, what is happening is I added something here. I said, okay, 35 plus 2 or 35, or let's say 33 plus 2. Okay. And suppose there was a ladder here, right? It's not going to take you out. But what I'm checking is that when I'm adding this value board of j, j must be less than destination. And when I'm adding the edge, that edge must be less than destination. Let me run the code. Okay, so I think I commented out the shortest path. Let's rerun this code and it should be good to go now. So we do not need to print each and every node while traversal, right? One more attempt and then we should be good to go. We are doing BFS, we are printing the output of traversal, which we don't want. So let's paste the code and here we are getting, yes, this is the correct output. So we are getting the path and we are getting the shortest length, that is going to be 4. If I show you, this is the path that we are getting. From 1 we went to 15, 29, 30 and 36, and it took 4 number of moves. 4 moves were required to cover this. You can verify also. 1, 15, 29, 30, 36. From 1 we went to 15, then we went to 29, then we went to 30 and then we went to 36. Yes, these are the 4 moves that were used. So I really hope you understood this algorithm really well and the application of BFS we have seen through this problem. So that's all for this tutorial. If you like the video, please make sure you subscribe to our channel and I will see you in the next tutorial.